Today we shall discuss about coherent state structure of pseudo-Hermitian Hamiltonian system with position-dependent effective mass. So here the abstract of my talk, that the exact solvability of pseudo-Hermitian Hamiltonians for position-dependent effective mass system is revised with the aid of supersymmetric quantum mechanics formalism. A class of pseudo-Hermitian Hamiltonians can be factorized. And it turns out that under a deformed algebra of generalized position and momentum, the coherent state structure of the system exists. So the first slide is just to fix up the notations, because these are well-known things. The possible state of a quantum mechanical system will be denoted by the vectors psi I, uh, uh, which belongs to some Hilbert space corresponding to the system S. And prior to your measurement, you know that the system remains on the superposition of all possible states. Measuring process are described by the action of operators acting on H. The eigenvalues of the operator under process appears as the experimental outcomes with some probability. The operators associated with the energy measurements are called the Hamiltonian of the system. The dynamics are governed by the Schrodinger equation H psi equal to I H cross del psi del T. So we shall confine the system, confine on the operators with which are Hamiltonian-like. That means which governs the dynamics of the system, and the eigenvalues of which will be termed as energy. And the necessary properties of a measuring operator should be that the expectation values should be real number, because since the measurement process is intrinsically probabilistic, we shall only get the expectation values, is the meaningful concept. So that should be real number. And on the other hand, it should necessarily provide the sharp collapse to a state after a measurement process, because otherwise the measurement process will not be that much meaningful. So spectral decomposition in terms of projectors and real eigenvalues are necessary for a meaningful operator. Um, and probabilities are associated with the norm of the vectors. Therefore, in order to total probability to be conserved under time evolution, the time evolution operator should be unitary. For example, for time-independent self-adjoint operator, H e to the power minus IHT by H cross is a evolution operator. This is unitary. However, from this perspective of probability conservation, norm conservation, the unitary evolution guarantees that the probabilities will be conserved. That means the existence of self-adjoint operator will guarantee the conservation of probability. However, the converse, that conservation of probability does not necessarily indicate that the H should be self-adjoint. Uh, and the adjoint operator O bar of an operator O will be defined by the usual inner product UOV equal to O bar UV, where V is the vectors belong to the Hilbert space and U are belongs to the adjoint space, and we shall use the inner product by this first bracket within, and the vectors will be separated by commas, and norm will be denoted by double vart of vector W, and since it's the Hilbert space, the norm can be defined through the inner product by the square root of inner product of the vector which itself, and the expectation values will be defined by the Rayleigh quotient, which is defined by the psi O psi by norm of psi square. If the operator is self-adjoint, one can show that the expectation values are real with respect to the inner product. And since the operators are defined by this, the adjoint is defined by this relation, by this inner product, it's not difficult to understand that the inner product plays a vital role in order to be a operator self-adjoint or not. For example, under the usual inner product, which I have shown on the previous slide, this operator, this the harmonic oscillator or ordinary harmonic oscillator Hamiltonian, added some symmetric Hamiltonian, but non-self-adjoint in the sense of the user inner product. One can show that this. In fact, it's not straightforward to show that the adjoint of this operator is this. That means this minus gamma half plus x ddx will be replaced by gamma half x ddx. So if gamma not equal to 0, this is not a self-adjoint operator with the usual inner product. However, if we deform the inner product uh, with introducing some operator t e to the power gamma 2 gamma x square and redefine the inner product as utv, then one can show that this operator is self-adjoint under this inner product. So inner product plays a vital role in order to be operator self-adjoint. And these are the just to fix the notation that a linear operator is we shall denote as pseudo-Hermitian if an invertible Hermitian operator eta exists such that the adjoint operator of H is connected to eta H eta inverse. For example, the PT symmetric Hamiltonians are pseudo-Hermitian. And actually, the PT symmetric Hermitian operator are actually Hermitian operator is necessarily in disguise because it's nothing but a similarity transformation. So up to similarity transformation, the physical theory should be regarded as equivalent. So actually, the pseudo-Hermitian operators are basically Hermitian in disguise. And for our purpose of today's talk, we shall start with the Hamiltonian. This is the position-dependent effective mass Hamiltonian. This is the kinetic part, minus h cos square by 2 ddx of 1 by m ddx. This m is the position-dependent effective mass. And the form of the position-dependent effective mass is well known in regard to the position-dependent effective mass. There are numerical articles in the literature which fixed this the kinetic part of the sensible Hamiltonian, and this is of course this part is sensible under usual dot product, this inner product, and we have considered the perturbation like Swanson type, which was discussed for the transition probability in atom long back 2004. And this nu and nu zero will be R. And further, for simplicity, I'll assume that nu is non-zero, so that this is PT symmetric and the total Hamiltonian is as well PT symmetric. And there's an V0x external potential that should be any type of potential, but we shall see that only specific type of V0x and MX will provide the coherent state structure and will provide the sensible transformation operator eta. So under the usual inner product, the adjoint of this operator is this. The minus mu zero goes to mu into 1 minus mu zero, and x minus x ddx goes to plus x ddx. So this is not self-adjoint under this inner product. And I shall further restrict on the constraint that mod of mu will be very, very less than 1, so that the perturbation will not completely destroy the original behavior of our original system. Original system means this the kinetic part plus V0. This is the original system. This is the position-dependent effective mass placed in the external field V0x. And this added perturbation is symmetric and responsible for non-hermiticity, the usual dot product. So our task is to find out some sensible metric operator eta h, which connects the adjoint of H, and H and H0 is connected through eta H eta inverse. This is the adjoint. So in order to construct the eta, we consider the answers e to the power some function of x. in the literature, it is known that often the choice e to the power some operator for the metric operator is helpful. So under this choice, the transformation rules becomes uh, this. A kinetic part will remain the same, and there will be some added term. There's this term plus this term, and this lambda prime by m ddx plus some added x dependent terms will be appeared. And in order to do this calculation, it is if one use the Baker's house of relation, that is e to the power lambda h e to the power minus lambda equal to h plus commutator of lambda h plus 1 by factorial 2 lambda lambda h. Up to these terms, it will be vanished, and this simple calculation will provide this equation 13. This is the adjoint of h under this transformation. And in order to make it self-adjoint, so this was our original Hamiltonian. So minus mu 0 x plus x ddx. So minus mu x ddx, and there is another ddx term. So if we restrict that, this summation of minus x ddx and summation of lambda prime by m ddx vanishes, because we are going to we construct lambda. So we have we are free to restrict ourselves with our suitable domain. So let us do that. That is this lambda prime equal to some nu by h cos square x times m. That means that is lambda prime equal to x times m, means this is m, mm goes up. So this is x ddx, and this will goes up. Um, so this choice of lambda will give that h is a self-adjoint with respect to the dot product eta um, u eta square u d, and this added term lambda 1, this lambda 1 looks like this. This is basically a combination of lambda prime and lambda prime square with the coefficient depending upon the position dependent effective mass. So from equation 15, one can solve for lambda, and which is integration of x into m dx with up to some added constant, which will be set to 0 for simplicity, because if one set is non-zero, it can be easily absorbed in normalization factors, so it doesn't matter at all. So we'll restrict ourselves for lambda 0 equal to 0. And the choice of lambda x, that is integration xm, will reduce h0 to this minus h cross square ddx of 1 by m ddx minus mu 0 plus v1x, which is self-adjoint, and v1 is our old potential plus some added added potential depending upon the effective mass. And if m is constant mass, usual constant mass system, then this is nothing but a harmonic oscillator term, because m is constant and this is constant time x square harmonic oscillator, and m prime goes to 0. So this is this transformation will arise, will provide just a harmonic oscillator term. So that's why in literature it is widely used that the position dependent effective mass in terms of symmetric operator, the people usually solve the harmonic oscillator potential, so that actually this x square arise from the transformation, and x square that will effectively gives nothing in result. But if we restrict ourselves with some extra general v0x, then the situation will be more complicated and interesting. And so this equivalent Hamiltonian H1 can be solved exactly for specific type of V, of course, with some equivalent constant mass system, and we shall discuss this now. This is our original Schrodinger equation, time independent Schrodinger equation. This is the kinetic plus some, this is our reduced potential times wave function equal to eigenvalue times wave function is the eigenvalue equation. In order to solve this eigenvalue equation 19, we consider that this system is equivalent to some constant mass system. Let us fix that this system is equivalent to the constant mass system. This for constant mass system minus d to dy to psi n plus v psi n equal to en psi n. This is v is the potential for constant mass system, and we have for simplicity, because this is equivalent system, so we can freely choose the mass to unity, and we have done this. And this, if we know the solution of this system, then with the help of the solution of this system, one can reduce the solution of this system, provided one is equipped with the transformation rules. So let us assume that the transformation rule is that is the new variable y is related to x by some transformation y equal to fx, and the new wave function, there's a wave function for equivalent position independent mass, is related to the wave function of position dependent mass by some scaling factor gx sin tilde x. So in order to this equation will be consistent, one can show that this constraint should be satisfied. That is, a prime should be square root of m, and the g, the scaling factor g, should be 1 by m to the power 1 by 4. And these are isospectral, that is en and en tilde are equal. And v tilde x, the y v tilde equal to v of f plus 1 by m into m double prime by m minus 7 by 4 m prime by m whole square. So it's a well-known result. And so one can see that under that if one restrict v tilde, then the v will be a very specific type. If v tilde is fixed, then one can solve in terms of v from this equation. So v will be very
Pinaki?
specific. But yes.
Yeah. Hi. Actually,
yes.
So we are slightly running out of time. So if you could please.
Okay.
Yeah. Thank you.
Okay. So, but okay. So so in despite of the general v tilde, I will consider that since this is a tractable equation, so we will confine that Vy is known the reverse way. Vy is known, and we will see for which v tilde x this Vy is sensible. So we will adopt the reverse way. So let V is harmonic oscillator type, so that we will find that which v tilde is responsible for equivalent harmonic oscillator. So if we consider that v tilde V is harmonic oscillator type, one can see that the M and the v tilde will be this type. This is M is some inverse of x 1 plus x to the power 4 by 3 with some parameter, so that the parameter goes to 0 will provide the constant mass case, and the transmission rule reduced to this, and the effect, the external potential will be confined to this x to the power 2 by 3, and v0x will be this. So the non-equivalent position independent mass system, the wave function is given by e to the Gaussian type times Hermite polynomials with energy n plus half h cos beta, and the position dependent effective mass system will be the eigenstate of position dependent effective mass system will be 1 by g psi n of fx. And for example, for ground state system, for ground state, the wave function is 1 by 1 plus beta x to the power minus 1/3 e to the power minus 1 plus beta x to the power 2/3 with same eigenvalues. This is the ground state for position-dependent effective mass system. So ground state is important because we are going to apply the supersymmetric quantum mechanics formalism. So in supersymmetric mechanics formalism, we confine that, we restrict that the system is equivalent to some equivalent system with some different potential B2x, and these are connected with some intertwining of relation AH1 equal to H2A, and we have to find out this intertwining operator for this sensible supersymmetric formalism. And if A can be regarded as the annihilation operator, the eigenstate of this A will give the coherent state. So if we take the answers A ddx of A plus phi, then the commutation relation between A and its adjoint is phi tilde by L over M. For constant mass system, this is nothing but some identity. But under this deformed algebra, one can regard that A is an annihilation operator. And if we use this intertwining relation with this two Hamiltonian, one can show that A should be 1 by m to the power 1 by 4th, and the new potential and old potential will be related with equation 44. And from constancy Riccati equation in terms of the ground state minus u prime by u will be obtained. This Riccati equation will be solved, can be solved for a given m, and our m is given. This is 1 by x to the power 4 by 3. So one can solve this Riccati equation. In general case, one can solve this in principle, but for arbitrary case, it is very difficult to solve. So the partner potential, the superpotential is k square minus a prime, and this is reads like this: 1 by 1 plus beta x and 1 plus 1 by beta x equal to 1/3. And the the superpotential explicitly reads as this: 1 by x to the power 1/3, 1 by x to the power 11 by 6, and 1 plus x to the power 1/3. And the desired coherent state will be like this. That is zeta to the power 1 by 3, zeta to the power 2 by 3, and zeta to the power minus 3 by 3 with some coefficient 1 by zeta to the power 2 by 3, where zeta equal to 1 plus beta x. And one can show that this is indeed a coherent state. And in conclusion, that we have seen that the coherent state structure can be constructed for position-dependent effective mass in H Hamiltonian scenario. First step is to find a metric operator associated with the Hamiltonian in order to make it self-adjoint. Then the eigenstate of the system is constructed with the help of an equivalent constant mass system. An annihilation operator can be constructed for the PDM system with the aid of supersymmetric quantum mechanics. The eigenstate of the annihilation operator are the desired coherent state. Thank you. Any question, please?
Yeah, thank you. Thank you, Pinaki. So are there any questions?
Yes.
Yeah, please go ahead. Yes.
Sir, actually, you are dealing with position-dependent mass systems, in which you have related two different Hamiltonians through similarity transformation, that eta, but here the eta is a real one, and you consider it which includes mass functions, isn't it, sir? Sir, actually, my first doubt is both the Hamiltonians, though it is Hermitian and non-Hermitian, both are related through similarity transformation. They possess a real energy spectrum, isn't it, sir? If one admits, if one admits real energy spectrum, the both admits real energy spectrum. It should be modified with respect to metric, isn't it, sir?
Yes, it will be part 2 gamma x. Yeah. So that's immediate.
Yes, sir. Suppose if the Hamiltonian, non-Hermitian Hamiltonian admits real energy spectrum, which is square integrable in its own space, minus infinity to infinity. There is no appearance of that metric operator. It's still acceptable, sir.
The last line I didn't get.
Actually, if the system, the Hamiltonian, it's a non-Hermitian one, admits real energy spectrum and eigenfunction which is square integrable in a real space, minus infinity to infinity. Okay, sir. But there is no need, it doesn't include that metric one. Do you come across that kind of system, sir? It's a little bit complicated doubt, actually, I'm asking. Sir, actually, it is mandatory that eigenfunction is square integrable with respect to its deformed Hilbert space, deformed metric.
Yes, the existence of the real eigenspectrum for the deformed space,
Yes, sir.
the existence of the real eigenvalues in the deformed space is not guaranteed for unbounded eta. For example, the eta I have considered is basically not bounded.
Yes, sir. Yes, sir. Okay, sir.
So it is not guaranteed. But for bounded eta, it is guaranteed that the deformed space will provide the real eigenspectra. But for unbounded eta, you have to calculate the eigenspectrum different. You have to check whether the eigenspectrum is real or not. In our case, in the particular problem, this is the case that the eigenspectrum is real. But for in general case, where eta is unbounded, it is, I don't know whether it is guaranteed or not.
Okay, so actually it is not a mandatory one. It is not a rule. We can get a real energy spectrum.
Okay, so maybe
Thank you, sir.
yeah, so maybe you can continue this discussion, the discussion by email and this thing. So we are running out of time. We are very late. So thank you, Pinaki. Thank you very much for the talk. And